You know the dream. It's a staple of pretty much every space opera ever written, from Star Trek to Interstellar.
Oh, absolutely.
You're the captain of a starship. You need to get from Earth to, I don't know, the Vega system, which is 25 light years away. The aliens are closing in, the shields are failing. So what do? You fire up the drive, punch a hole in the fabric of space-time, and jump.
It's the classic sci-fi shortcut. It's really the only way you can have a galactic civilization without everyone, dying of old age during the commute.
Right, it's the ultimate travel hack. But today, we are definitely not talking about movies. We are looking at the hard reality. We're asking the big question. Is this just Hollywood magic, or is it actual real-world physics? Do wormholes actually exist?
It is the ultimate question for anyone who looks up at the stars and feels a little impatient, and to anchor us right at the start. The answer is a very complicated maybe. We haven't found one yet, we haven't seen one, but general relativity, the very same theory that predicted black holes, does mathematically allow for them.
So the math says yes, but the universe is, what, playing hard to get?
In a sense. Our mission for this deep dive is to sift through all the, the wishful thinking and the hard math. We need to figure out if these things are physical realities we could actually travel through, or if they're just mathematical ghosts.
Artifacts in the equations.
Exactly. Things that don't actually correspond to anything real.
Okay, let's unpack this. Because I think most of us have seen that movie scene, where the scientist grabs a piece of paper and a pencil to explain it all.
The folding paper analogy.
They draw 2 dots on a page, say this is point A and this is point B. The distance is too far to walk. So they fold the paper in half, punch a pencil through the 2 dots, and voila, the distance is now 0.
Works great on paper.
But we don't live on a sheet of paper. Does that analogy actually hold water when you apply it to the real universe?
It holds up surprisingly well, actually. But you have to shift your perspective. You have to stop thinking of space as just this empty nothingness and start thinking of it as a fabric.
Like in Einstein's general relativity.
Right. Space and time are flexible. They can warp, bend, and curve.
Yeah.
And the idea is that if you curve space-time enough, 2 points that are billions of light years apart in normal space could actually be connected by a tunnel, a shortcut.
And that tunnel is the wormhole. But I was surprised to learn from the materials that this concept wasn't just invented by some sci-fi writer. It's way older.
Oh, much older.
Yeah.
We have to go back to 1916. An Austrian physicist, Ludwig Flamm, was looking at the equations for black holes, which were brand new at the time, and he realized the math was hinting at some kind of connection. But the real heavy hitters came in 1935.
Einstein himself.
Einstein and his colleague Nathan Rosen. But here's the funny thing. They weren't trying to build a subway system for spaceships. They were just trying to solve a problem with particles. They were trying to get rid of singularities.
So they weren't even looking for a travel method.
Not at all. They were just trying to clean up the math. In the process, they discovered this mathematical structure that connected 2 different points in space-time. But they didn't call it a wormhole. They called it an Einstein-Rosen bridge.
Which sounds very, very formal.
It gets worse. In the early papers, they were described as one-dimensional tubes.
Captain, set a course for the one-dimensional tube. That really kills the vibe.
It lacks a certain romance, doesn't it? The term wormhole actually didn't appear until 1957. It was coined by the physicist John Wheeler.
And he's the one who gave us the apple analogy.
Yes, which I think is arguably even better than the paper folding one.
Okay, walk us through that one, because when I think of worms and apples, I usually just think about throwing the apple away.
Well, imagine the universe is just the skin of an apple. If you are an ant crawling on the skin, and you want to get from the top to the bottom, you have to walk all the way around the curve. That's the long way.
That's us, traveling through normal space.
Right. But if a worm were to bore a hole straight through the middle of the apple,
The worm beats the ant.
every time. The wormhole is the tunnel through the bulk of the apple. Wheeler was brilliant at these visualizations. It's also just worth noting, for the literary folks, that this idea of a bridge between worlds actually predates the physics in fiction. Lewis Carroll's Through the Looking Glass is often cited as the first fictionalized wormhole.
A mirror that's a bridge to another reality. I love that Alice in Wonderland beat Einstein to the punch. But let's get visual for a second, because in my head, a wormhole is a swirling whirlpool in space. Like a drain.
That's the common depiction, yeah. But if you think about the geometry of it, it's completely wrong.
Wrong how? If it's a hole, shouldn't it look like a hole?
Well, think about a black hole or a planet. They aren't flat disks, they're spheres, right? A wormhole would be similar. Space is 3-dimensional. So if you punch a hole in a three-dimensional universe, the hole itself is a sphere.
Okay, I'm trying to picture this. If I'm in a spaceship flying up to this thing, I wouldn't see a flat tunnel. I'd see a ball.
You see a spherical distortion, like a crystal ball just floating in space. And here's where it gets really trippy. You would be seeing light from the other side coming out of that sphere in all directions.
One of the articles described it as getting sucked into a ball and expelled from another ball.
You have the mouth of the wormhole, which is the sphere leading into the throat. That's the narrowest point connecting the two mouths.
So wait, Interstellar actually got it right with the sphere.
They did, and that's largely thanks to Kip Thorne, a Nobel Prize-winning physicist who was an executive producer on the film. He insisted on the physics being accurate. So when they show the wormhole as a sphere distorting the stars behind it, that is the most scientifically grounded depiction we have.
Okay, so we know what they are, we know what they look like, and we know the math allows for them. Here's where it gets really interesting for me. If the math works, and we've known this since 1935, why aren't we commuting to Alpha Centauri right now? Why is this still just a theory?
Because there's a huge difference between mathematically possible and physically survivable. The original Einstein-Rosen bridges, those 1935 models, they had a fatal flaw.
The snapshot problem.
Exactly. The math shows that an Einstein-Rosen bridge is incredibly unstable. If you were to try to cross one, the throat would pinch off. You would collapse faster than the speed of light.
Wait, faster than light. So it's not just that the bridge falls down, it's that it closes on you.
It's worse than a bridge falling down. It's a cosmic guillotine. The moment a single photon of light tries to enter the throat, the gravity of the wormhole reacts violently. It pinches shut instantly.
So you wouldn't even make it across the threshold.
You'd be crushed into a singularity before you got there.
So it's a trap. It looks like a door, but it's actually a meat grinder.
Essentially. For decades, that was the consensus. Wormholes exist in the math, but you just can't use them. But of course, physicists didn't give up. And this brings us back to Kip Thorne again. In the late 80s, he and his student Michael Morris decided to treat this as an engineering problem.
This started because Carl Sagan needed a plot device for his book Contact.
Right? It did. Sagan wanted a realistic way for his character to travel, so he asked Thorne. And Thorne and Morris looked at the equations and asked, okay, the throat wants to snap shut because of gravity. What would it take to keep it open?
Something to hold the walls of the tunnel apart.
Exactly. And the answer they found is one of the wildest concepts in physics. Exotic matter.
Okay, exotic matter. Now hold on. That sounds like a cheat code. It sounds like something a writer just made up to fix a plot hole. Is this real physics or is this just unobtainium?
It really does sound like fiction, but it has a very specific definition in physics. The problem with the wormhole is gravity. Mass attracts mass. Gravity wants to pull the walls of the throat together. So to keep it open, you need a force that pushes back. You need anti-gravity.
Propulsive gravity.
And to get repulsive gravity, you need matter that violates something called the null energy condition.
Yeah.
Basically, you need matter with negative energy density.
Let's pause there. Negative energy. I get negative numbers in a bank account, but negative energy in the real world, how does that even work?
It's a weird concept. Don't think of it like a battery charge. Think of it more like pressure. Imagine the wormhole throat is a balloon deep under the ocean. The water pressure is gravity, crushing it from all sides.
Okay.
To keep that balloon inflated, you need to fill it with something that pushes outward harder than the ocean pushes in.
And that something is exotic matter.
Yes. Normal matter, stars, planets, you, me, we all have positive energy. We pull things in. Exotic matter has negative energy. It creates a repulsive pressure that pushes space-time apart. It's the air in the balloon holding back the crushing ocean of gravity.
But does this stuff actually exist? Or is it just a variable in an equation that we've never found in the wild?
It's not totally fantasy. We actually see hints of negative energy in quantum mechanics. There's something called the Casimir effect.
The thing with the two metal plates.
That's the one. If you take two metal plates and put them extremely close together in a vacuum, the quantum fluctuations between the plates are restricted compared to the fluctuations outside. This creates a pressure difference. The space between the plates effectively has a tiny amount of negative energy density.
So we can make it.
On a microscopic quantum scale.
Yeah.
But here is the massive buzzkill.
Yeah.
To hold open a wormhole big enough for a human, you would need a Jupiter-sized amount of this negative energy.
A Jupiter-sized amount.
And we have absolutely no idea how to manufacture or collect that. We can make a tiny blip of it in a lab, but scaling that up to a galactic transport system. As one researcher put it, that would require magic or a civilization a million years ahead of us.
Okay, so building one is out. For now, we just don't have the exotic matter to prop the door open. But nature does crazy things all the time. Could there be a wormhole hiding in the dark somewhere, naturally occurring?
This is where the hunt moves to the center of our galaxy, to Sagittarius A star, our supermassive black hole.
And some physicists think that might actually be a wormhole.
Or that there might be one nearby. A physicist named Dejan Stochkovich and others have proposed a way to test this. They call it gravity leakage.
I like the analogy of the fishing line for this. Can you explain that?
Yeah, so imagine you have a wormhole connecting our galaxy to some other distant galaxy. And imagine there are heavy stars or black holes on the other side of that wormhole. Gravity can travel through the tunnel.
Right.
So if you're standing on our side, you might feel a gravitational tug from an object that isn't actually there.
It's like feeling a tug on a fishing line that goes through a hole in a fence. You can't see who's pulling, but you know someone is there.
That's the idea exactly. Stochkovich suggested looking at the stars orbiting Sagittarius A star, specifically a star named S2. If S2 wobbles in its orbit in a way that can't be explained by the black hole alone, if it feels a gravitational tug from nowhere, that could be evidence of a wormhole.
A ghost pulling on the star.
The deviations we're looking for would be about 10 million times weaker than Earth's gravity. Our current instruments just aren't quite sensitive enough. It might take another decade or two of observation to rule it in or out.
Is there any other way to spot them? What about, just looking for them?
We can look for gravitational lensing. Black holes bend light like a lens. A wormhole would also bend light, but differently. Because of that negative energy, that repulsive gravity, a wormhole wouldn't just focus light. It would create a very specific signature.
What kind of signature?
If a wormhole passed in front of a distant star, the light wouldn't just get brighter. It would brighten, then fade, then brighten again in a really distinct pattern.
So we have a mugshot, but we haven't found the suspect.
Correct. It's like searching for a needle in a haystack made of needles.
So we can't build them yet, and we haven't found a big one yet. But wait, there's a plot twist in the research, a massive one. What if we've been looking at this all wrong? What if wormholes aren't these giant tunnels for spaceships, but are everywhere, stitching the universe together?
This is one of the most exciting and frankly mind-bending shifts in modern physics. It's called ER equals EPR.
Which sounds like a secret code.
It basically is. It stands for Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations.
Okay, you have to translate that for us non-Nobel winners.
Einstein-Rosen bridges are wormholes. Einstein-Podolsky-Rosen refers to quantum entanglement.
Ah, entanglement. Spooky action at a distance, right? You affect one particle, and its partner instantly reacts, even if it's on the other side of the universe.
Exactly. And for a long time, physics has been at war with itself. We have general relativity for big things like gravity and wormholes. We have quantum mechanics for small things like atoms and entanglement. And they hate each other.
They don't play by the same rule.
At all. But EPR says they might be the same thing. Juan Maldacena and Leonard Susskind proposed that they are physically equivalent. They suggested that when two particles are entangled, they're actually connected by a microscopic wormhole.
Wait, so every time particles are entangled, which happens constantly, there's a tiny wormhole connecting them.
That's the theory. Wormholes aren't just these rare exotic anomalies. They might be the fundamental threads that stitch space-time together.
That completely changes the picture. It means the sci-fi dream of a tunnel through space is kind of happening constantly, just at the atomic level.
And it solves a major headache for physicists, the information paradox.
Stephen Hawking's famous problem.
It is. So here's the mystery. Black holes swallow things. If you throw a book into a black hole, the information in that book seems to be gone. But Hawking also proved that black holes eventually evaporate and disappear. So when the black hole is gone, where did the book go?
Quantum mechanics says information can never be destroyed.
Right, so you have a paradox. It's like a locked room mystery where the body vanishes.
And EPR provides the secret tunnel out.
That's the idea. The theory suggests the interior of the black hole is connected to the radiation escaping it via these microscopic wormholes. The information isn't lost, it's just scrambled and accessible through these quantum tunnels.
So wormholes save quantum mechanics.
Theoretically, yes.
It sounds perfect. It ties everything together. I feel like we're getting too comfortable. There's always a skeptic in physics. There has to be someone saying, stop having fun, this is all wrong.
Oh, there's always a skeptic, and for good reason.
Yeah.
We have to look at the mathematical artifact argument. People like Espen Gardner Hogg argue that wormholes don't exist at all, period.
What's their argument?
They look at the math differently. They argue that in newer, more unified theories, or when you strictly apply relativistic mass, the math for wormholes just breaks down.
Is this the division by zero thing I read about?
It is. In the classic equations, the term that allows the throat to exist works fine. But when you apply these other constraints, that same term results in a division by zero.
And for anyone who's used a calculator, division by zero just means error.
In physics, it's a singularity. It's a do not enter sign from the universe. It implies the structure is mathematically impossible. The argument is that just because general relativity allows it, doesn't mean nature actually uses it.
Like how I can type -$1 million into a spreadsheet, but that doesn't mean the bank is going to give it to me.
Precisely. General relativity also allows for closed time-like curves, which are literally time machines. But most physicists believe causality prevents them from existing. Just because the equation has a solution doesn't mean the universe builds it. We might just be chasing a ghost in the machine.
That's a sobering thought. We might be studying a glitch in our own math.
It is possible. But even if they are glitches, look at where they've taken us. We went from one-dimensional tubes in 1935 to worms in apples in the 50s, to quantum threads knitting the universe together today.
Even if we can't fly a ship through one, the idea of the wormhole has forced us to understand gravity and quantum mechanics in ways we never would have otherwise.
That is the real value. Whether they are traversable tunnels or just quantum links, studying them pushes the boundaries of what we know about reality.
Before we wrap up, I want to leave everyone with one final, slightly terrifying image from the research. It's from something called the Randall-Sundrum model. They describe a specific type of traversable wormhole as the ultimate roller coaster.
Oh, this is a fascinating concept.
The idea is, if a human traversable wormhole did exist, one big enough to fit us, you wouldn't need a rocket engine to get through it.
No, the gravity of the wormhole itself would do all the work.
You would be accelerated to these incredible speeds by gravity alone, shot across the universe, and then decelerated on the other side. And because of the way space and time are warped inside, this whole journey would take maybe a fraction of a second of your time.
But, and this is the kicker, while it takes a fraction of a second for you, eons might pass outside.
You arrive instantly, but you arrive in the far, far future. Everyone you knew is gone. Civilization might be gone.
It brings a whole new meaning to seeing the future. You're not just traveling through space, you're traveling through time.
Talk about a one-way trip. I think I'd let a probe go first.
I think that is the safest bet.
Well, on that existential note, thanks for taking this deep dive with us into the weirdest corners of space-time.
It was a pleasure.